Welcome to this morning's Center of Excellence seminar. Our speaker this morning is Professor Anke Kalauch from TU Dresden. She works in pre-Reisz spaces, partially ordered spaces, partially ordered vector spaces, and various geometric objects like polytopes on and off, and all manner of interesting different structures that live largely within functional analysis, but can be viewed from many different aspects, algebraically, geometrically, and things like that. But today she will be talking about Reisz homomorphisms and other order-preserving structures. The title correct. Thank you.
Yeah, Bruce, thank you very much. First of all, I would like to thank my great hosts, Bruce Watson and Wenjin Ku, for this very pleasant stay here at Reisz University. And it's always a pleasure to be here in South Africa. Yeah, as Bruce already said, my main topic are Reisz homomorphisms that preserve the basic structure of vector lattices. And in vector lattices, in the classical theory, it is well known that every Reisz homomorphism is a positive operator and it is disjoint preserving. I will give you all the definitions, the detailed definitions in a few minutes. And there is a second result in the classical theory which represents these Reisz homomorphisms on spaces of continuous functions. So as the simple example of lattices, please think of spaces of continuous functions. These are these CP, CK spaces here. Consider a linear operator there. And it is in Reisz homomorphism, so such a structure preserving operator, if and only if we find an alpha and map alpha that just moves around the underlying points, and we find a weight function, and the operator has been given by this. This is the characterization for Reisz homomorphisms in this very classical case. And since the since the 90s, there were several efforts to extend this notion of Reisz homomorphisms to the more general case of ordered vector spaces. So spaces which have still a partial order that fits to the vector space operation, but lacks the lattice property. So in the 90s, Buskes and von Roy gave a certain notion, Reisz homomorphisms, von Handel as well, Reisz star homomorphisms. In 2006, we started the disjoint preserving operators with a colleague of mine, Onno van Gaans from University of Leiden. And some observations of Van Handel had some gaps which we could fill very recent in a work last year. And if I would just give you the definitions of all these types of operators, you just see a kind of a mess of upper-lower bouncing. So when we want to replace the supremum, then we have to replace it by upper-lower bounds. What I want to do today is just give a survey, an overview, and explain where these definitions come from. So I would like to give a basic talk. Yeah, and then I would like to show you the relations between these operators, the properties, and if we are in the case of continuous functions, can we get similar representations, yes or no? So this will be roughly things I want to talk about. The whole subject I consider together with Onno van Gaans from Leiden and with my students, Janko, Florian, and I. Okay, so let's start with the basic things. We consider a real vector space, and we take a partial order on this vector space, and this partial order should fit to the addition in the vector space as well as to the scalar multiplication in a good way. And if you have such a partial order, then we can look at all elements that are greater or equal than the 0 element in the vector space here. And it turns out that this is a cone. meaning that if I add two elements, then I stay in the cone. If I multiply with a positive scalar, then I stay in the cone. And it does not contain a linear subspace. So if I intersect it with minus k, then it's just 0. The vector space of such a cone, we call it an ordered vector space. And from the axiomatic introduction of real numbers, you know Archimedeanity, and you can translate it in a very similar way in these ordered vector spaces. So we have these the class of Archimedean spaces, which is a very large class. And among the ordered vector spaces, we are mostly interested in the case where the whole space is given by k minus k. This is equivalent to this space being directed. So in vector lattices, we have the supremum. In ordered vector spaces, we don't have the supremum in general. So we will need sets of upper bounds of the set and sets of lower bounds. Ordered vectors. And only in very special cases, namely here in the first case, you can find infimum and supremum of any two elements. So the other three objects are ordered vector spaces or cones in ordered vector spaces, but they are not vector lattices. The only vector lattice is this object. I show you why, just geometrically. When you take the Fourier cone, the second example, and you look at all the upper bounds of two elements, sometimes, like in this case with x and y, the set of upper bounds, this is this cone here, has the smallest element, so the supremum of the two elements exists. Whereas in the other case, when you look at x and u, and look at this set of upper bounds of the two elements, you will not find the smallest one. So here you see this has a natural partial order. No, you can talk about the sets of upper bounds of elements, but you have elements which don't possess a supremum. So this is a simple example, geometric example. You will see that the world of lattices and the world of ordered vector spaces are different. Vector lattices are very nice. Yeah, in vector lattices, I have supremum everywhere. So I can look at the supremum of an element and 0, which I call x plus, and element of minus x, which I minus the element and 0, call x minus, and the modulus. So here I have the x plus, x minus, and the modulus of every element. And this makes the whole theory of vector lattices so nice. Yeah, you can calculate almost as in the numbers. You don't have this in ordered vector space. So there we need different other approaches to deal with similar notions, also notions that are well known in lattice theory, and we want to make similar notions in ordered vector space. But we don't have the module anymore, we don't have the supremum anymore. We need some new ideas. I would like to explain you this basic approach about using the notion of disjointness. When you have functions, normal functions, yeah, on an interval, you have an idea of what disjoint should mean. Yeah, namely, one of the two, so say function g and a function f. First, that you have in mind what I mean. Yeah, you have a function f and a function g. And they are disjoint if at any point one of the two is 0. Yeah, you multiply them, then you get 0. So for function, you have an idea what disjointness means. So pointwise disjoint. In vector lattices, you look at the modulus of the two elements, and if the infimum of the two is 0, then this is a similar description of the idea you have in these function spaces. And in vector lattices, you have an equivalent notion that the sum and the difference have the same modulus. I already mentioned that this supremum does not exist in all function spaces. For example, if you look at C1 the differentiable functions, it does not exist in general. But you have the same idea of how two elements of C1, what the jointness means there. So the idea is to give a definition that fits to the standard definition for functions in a good way. And here you see, when you have any equation with modulus in it, no? The modulus is the supremum of x and minus x. And if you don't have supremum, just take the upper bounds of x and minus x, yeah? And this equality here is just an equality of sets of upper bounds. This is the basic idea. And with this idea, you can translate most of the notions in lattices to ordered vector spaces and do at least a part of the theory you have in the classical case. And with this, you also can define the joint complements and bands. It's the same as in the case of Archimedean vector lattices. So all these objects are there now. And therefore, you have a very natural extension of the classical disjointness preserving operators on lattices. You can do now the same on ordered vector spaces with this new notion of disjointness. Yeah. So a linear operator is called disjointness preserving if you start with disjoint elements, you end up with disjoint elements. And also band preserving is defined well now, means every band is into a band, itself. And these band preserving operators, these in the theory of Banach lattices, they are called local, are a special case of these disjointness preserving operators. Just as an example of disjointness preserving operators. So now we want to do something similar for these Reisz homomorphisms I was starting with. And if you want to replace the supremum there by sets of upper bounds, lower bounds, there are different approaches. We start with an approach that might be familiar to you. When you look at real numbers, then you look at Dedekind cuts. Yeah, what objects are they? These are objects, so subsets, where the set equals the set of first take the upper bound, then take the lower bound. Yeah, and you collect all these objects. This is what you do in the real numbers, and you can do exactly the same in these ordered vector spaces. The only structure you need is your partial order and the vector space structure. You order this set by inclusion. And to any point of your original space, you can look just at the set of lower bounds. The set of lower bounds is such a Dedekind cut because when you take here the upper bounds and the lower bounds, you end up with the same element. So these are Dedekind cuts you can embed in the classical way. And your set X delta has been called, it turns out it's a Dedekind complete lattice. This is not so difficult to prove. And this map is bipositive. So it is an embedding. An element here is positive if and only if you can introduce an ordering here. By inclusion, yeah. So an element is positive here if it is positive here. So it goes back and forth and it is embedding, it's injected. And you get an additional nice property, namely order denseness. The small space is order dense in the big space, meaning if you take an element of the big space in the big space y, take an element y, and you look at all elements of the small space being above this, and then take the infimum, you end up with this one. So this is order denseness. And this procedure can be done for any Archimedean ordered vector space. You could put an addition and scalar multiplication of this set X delta. So you end up with the complete. And the embedding map is linear. So, and this trick here with the upper lower bounds, we steal now to obtain definitions for the supremum we need for the Reisz homomorphism. So we just said every X induces a Dedekind cut and every set as well, take upper lower. And if you do this for finitely many elements, you need not, if you want the suprema of two of such Dedekind cuts, is just this object. And if you plug in these lower bounds of singular elements here, you can just take this. Exactly the same. This means that the supremum of two elements you can replace by x by x2 and then taking upper bounds and then taking lower bounds. And with this trick, we get several options. So this was the A, yeah, was the classical definition of the Reisz homomorphism in lattices. And now we just replace. Everywhere here we have where we have a supremum, we take here x1, x2 upper lower bounds. And here as well, and so we have to do it outside here as well. We can do it for two elements, we can do it for finitely elements in vector lattices. All this is equivalent. These are equivalent notions. So we will discuss in a minute how these notions relate in ordered vectors. So this is one approach, using Dedekind cuts for defining sort of Reisz homomorphisms in ordered vectors. There is a second approach. You take in A, so that when this is equal to this, you can also look at a set of lower bounds. Yeah, then they are also equal. And there's an equivalent characterization. So, and now we just replace the supremum just by the upper bounds. And this gives another notion, yeah, which is in vector lattices still equivalent to the Reisz homomorphism. Now let's. You can.
It's one of the constructions.
Yes.
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 This builds on that idea.
It's built on this idea. And this was done in the 70s by some Russian authors. It's really classic. Now I have to go back. So here's the overview of all. No, this one.
That's where you were.
That's where here we are. So the first approach led to the definitions in A and B, and so A is the classical one in lattices. B and C was the first approach by Dedekind cuts with finite with two elements or with finitely many elements. D was the second approach. And there are some, I wrote here B prime. This was just as it was introduced by the authors when it was used for the first time. Yeah, so there are equivalent conditions. So B, C, D is the stuff I just mentioned, and the rest is just equivalent. And in ordered vector space, so in ordered vector spaces, C and C prime is the same, B and B prime is the same, and B and D prime is the same. And one can observe C implies B, and D implies C. So what we have here now, coming back to the literature, B is exactly how Van Handel defined the operators, the Reisz homomorphisms he called. As C is the Van Handel. Yeah. Okay, here's the story. Van Handel defined it as B. He claimed to show that B and C are equivalent. And D was the were the Reisz homomorphisms by Duskis and Van Roy, the other sort of Reisz. But then it turned out that there was a gap in the proof to show that B and C are equivalent. And it was very recent that we could figure out that this is really not true. So these two objects are different. They are not the same. And I will show you an example in a few minutes. But what is true definitely is this implication here. So Reisz homomorphisms are V star, and V star are mild V star homomorphisms. And every of those is a positive operator, mapping the cone and the cone. And here, wait, I wanted to say, here I write previous spaces. So I short explain what it is. This was a notion introduced by von Handel as well. It's a characterization of spaces, again, using upper bounds, but don't worry much about this technical definition. The most important point for us was that all objects that are of interest, namely the Archimedean directed ordered spaces, are of this type. So we can use those, and all in the theory of operators, semigroups, etc. There are ordered Banach spaces with closed generating cones used, and all of those are Archimedean directed and hence previous, because the closed cone ensures Archimedeanity and generating cones the same. Order unit spaces we will discuss. So what is the nice thing about previous spaces? It is that these ordered vector spaces can be embedded order densely in an ambient vector lattice Y. So there exists a vector lattice Y, bipositive linear map, as in the case of the Dedekind completion we just had, such that the image under this embedding is order dense in Y. So we already saw that all these Archimedean directed spaces have the Dedekind completion, so they are order densely, can be order densely embedded. So they are previous spaces, yeah, but there are more previous spaces. And among all these order dense embeddings, you can kind of select the smallest one. You can really generate the lattice within the ambient vector lattice Y. And if you do this, then you get a unique object. So all these, doesn't matter which construction you use or with what ambient vector lattice you start, when you construct the smallest free space there, they are isomorphic as free spaces. So there you have a unique object, a unique lattice, a unique ambient lattice for every previous space. This is a nice thing to work with. So this Y, where I have this ambient vector lattice, I call vector lattice cover of X, and the smallest one is the Reisz completion. And the Reisz completion is in general much smaller than the Dedekind. Dedekind completion can be huge. And what was the reason for von Handel to introduce these three star homomorphisms? He had a real an aim to do this, namely, when you have this embedding into an ambient vector lattice, now you start with two previous spaces, you have ambient vector lattices, and he wanted exactly those operators who can be generalized, or can be extended to Reisz homomorphisms on these Reisz completions. Yeah, he wanted to characterize those operators who can be extended to the Reisz completion and ends up in a Reisz homomorphism there. And that's why he gave this technical condition with the upper lower bounds I gave you. Yeah, this was his reason to introduce this. So I told you what disjointness is in partially ordered vector spaces, and the nice thing is that this disjointness fits perfectly to this embedding of a previous space into the Reisz completion. So if I have disjoint elements in the previous space, it happens if and only if they are disjoint under this embedding in the ambient vector. And with this trick, one can translate classical theory in lattices to Reisz spaces back and forth. And the order denseness is needed for the one direction, otherwise you don't get it. One direction is true always, the other not. And now, if you have a Reisz star homomorphism, you can extend it to a Reisz homomorphism on a Reisz completion. Here it is a positive disjoint preserving operator. Yeah. And when you restrict, because of this nice property here, when you restrict, you end up with so the T where you start with is also disjoint preserving. So this gives you that every Reisz homomorphism is positive disjoint preserving. So you get this scheme. Viscous notion, Reisz homomorphism, von Handel notion, star, and all of those are examples of disjoint preserving. So I already mentioned order unit spaces. So the cones I showed you in the beginning, in finite dimensions. Note that these were closed cones and they have interior points. No? And these interior points, what property do they have? Every element in your space can be catched by this interior point from both sides. When you take the order interval, so you take lambda times this interior point and minus lambda this interior point, and lambda big enough, you will catch every element of your space. So the interior points of these cones are the so-called order units. This is just what's here. So any element is somewhere in this interval, minus lambda u, lambda u. And if I have such an order unit, this is very nice. I can look, what is the smallest lambda among all of those? And I can show, or one can show that this gives a nice norm on space. So when I have such an order unit, one is an interior point or so, just abstractly such an order unit, then you can introduce a nice norm on it, and then you call it an order unit space. And this works well for any Archimedean cone with order. This turns out to be a norm, and such spaces are called order unit spaces. And what can you do with those? The nice thing is, I will show you a picture in a minute. They have a very nice representation, and I would like briefly explain how this representation goes. You look at your dual, so you go to the dual space. You have a norm here, so you have the space of all linear continuous functionals on it. Classically, in functional analysis, you have the dual space. And you look at all those functionals that map the cone into positive numbers, so all positive functionals. And it turns out that this again gives you a cone. This is a so-called dual cone. And this cone is very nice. It has a base, sigma. I will show you a picture in a minute. So these are all that are one on your order unit. And the space has nice properties. It is weakly star compact, and so it can be represented by Klein-Millman theory by the set of extremes. I show you the picture first. So if you, for example, start with a circular cone here, yeah, this is K. This is the set of all K prime, set of all positive linear functionals. It turns out it has the same shape as, so the self-dual, it has the same shape. Yeah, the dual space is also R3. And the sigma is just this base of the cone. So every element of the cone you can get by a positive multiple of the set sigma, right? And if you do it for the Fourier cone, you get this set, the red one, as the sigma. Let's go back. So we have the sigma, and we can use Klein-Millman. So we can look at the extreme points of the sigma. This is in general not weakly star closed, not even if it is finite dimensional. I'll show you an example a bit later. And we can define, but this you have to close it, yeah. In the weak star topology, it's a compact Hausdorff space, and we can define an embedding of the x into the C of lambda bar, just by taking a functional and applying it to x, just a point evaluation. And this is again a bipositive embedding, maps u to the constant 1 function in the space of continuous function on this compact Hausdorff space. And it took us a while to show that this really is an order dense embedding. Was a joint work with a colleague with Bas Lemmens from University of Kent. So this gives really a vector lattice cover of the previous space. So C of lambda bar is in fact a vector lattice cover. So let's look at these pictures again. Here the lambda is just a set of extreme points. It's just a circle. Here it is are the 4 functionals F1, F2, F3, F4, extreme points of sigma. So you know exactly what the lambda or lambda bar is in these examples. So you can represent your order unit space as space of continuous functions on these sets. In the second case, it's just R4 with the standard form. Now you only have 4 points. It's very easy. So the interesting thing here is that, maybe we go here and back to the picture. These elements in lambda bar are exactly the Reisz homomorphisms. No? When you here you have a whole set of functionals, then you have the positive functionals, K prime, positive operators with range space R, yeah? And you can really see the Reisz and Reisz homomorphisms, namely, this is exactly the lambda. And here as well. So the Reisz homomorphisms is the lambda, so the functionals that are Reisz homomorphisms, and the functionals that are Reisz homomorphisms is the lambda bar. You can really see it. So this is this nice characterization. It's a classical result. The first is the highest Hayes theorem, was done in the 70s, and this is from Van Handel in the 90s. And now that we figured out that these mild Reisz homomorphisms and Reisz homomorphisms are not the same, we wanted to see it geometrically as well. We wanted to see it in these pictures, what are the mild Reisz homomorphisms. It was not so straightforward. But we got kind of a geometric description of it. So we are again in the sigma, we want to know what are the mild Reisz homomorphisms. And we have to use 0 sets of these elements. Show you a picture. Such an element, when you map it into your space of continuous functions, so to say, you can consider the element as affine functions on the sigma. So the violet one is an affine function on sigma. And for this element, you look at the 0 set and intersect it with the, you see, you intersect it with the extreme points and take convex hull and closure. This is here by Krein-Millman. But if you intersect it with the lambda bar, so if it is in ZX, then it should be in this set intersected with lambda bar, and this is in general not true. So here you see it has nothing to do with lambda bar, so this set is empty when you intersect it, so you don't get it back. So these objects are not on the red line, are not mild Reisz homomorphisms. And this you can rotate, you can do it almost everywhere on different places. The only points which are mild Reisz homomorphisms are just the same that are in lambda or lambda bar. So in this example of the Fourier cone, you end up that the Reisz homomorphisms, the mild Reisz homomorphism, mild Reisz homomorphism, and the Reisz homomorphism coincide, all the same. So this is one type of examples. Other type of examples, when you consider the circular cone again as affine functions over the sigma. You have again an affine function over sigma. You look at the 0 sets, and here you see when you intersect with the lambda is the circle, you get the set X back. So all of them, all element in sigma is a mild Reisz homomorphism. So this is the other extreme. Yeah. So lambda coincides with all mild Reisz homomorphisms. And I claimed that that all these notions are different. So I should show you an example where you see that all these notions are different. Yeah? Here these are a bit extreme examples. But in R3, you cannot find such examples. Yeah? In R3, you have either a strictly convex sigma, then you have the one case where sigma are all mild Reisz homomorphisms and sigma coincides, or not. Then you have the other extreme case. So in R3, only these 2 cases can happen. So we have to go to R4, and there one can give an example where all 3 notions are distinct. So we are in R4, yeah. So I have a cone there. We go to the dual cone again, and we look at the base of the dual cone, which has to be a 3-dimensional convex set now. What I was drawing here is just this dual set, the space of the dual cone. Yeah, this convex set. And again, what are the extreme points? That is easy here. It's F1, F2, and this circle, but not this point here. Yeah, this is not extreme because this is on the line here. So the lambda is just here the red without this point, and F1 and F2. This is the lambda. And you see when I close it, you obtain 1 point more. So the lambda bar is a little bit bigger, contains this point as well. And the mild V star homomorphisms, one can show that these are the D, so this the whole set plus the 2 points. This is a set of mild V star homomorphisms, but this is not the whole sigma. So, and this example showed us that this Van Handel proof was wrong from the beginning, yeah, when he claimed that mild V star and V star are the same. So now it's clear that they are all distinct notions, and we have this very nice scheme. If every Reisz is V star, every Reisz star is mild V star, and every mild V star is positive disjoint is preserving if the range space is an order unit space. This we could prove. So these mild V stars, these new objects, where we only use 2 elements for the definition and not finally many, fit in between Reisz homomorphisms and positive disjoint preserving. And all of those are distinct. So now I would like to talk a bit why it is enough to just consider these functionals. At the end, we want to have the relations between the operators. So arbitrary operators from one ordered space to another one. And there, again, we look at the cone of positive operators. So operators who map the cone of the first space into the cone of the second, these are called positive. And the K star is just the L plus of the all range R of the standard order. So, and some time ago, we observed it is totally enough that we consider the dual cone if there every Reisz star homomorphism is a Reisz homomorphism. So that means that lambda equals lambda bar. Then we get the same for operators. Yeah. So we need not investigate this. If you want to know whether these 2 notions coincide for ordered vector spaces, it's enough to check whether they coincide on the K prime, yeah, or even on Z. That's enough. We only have to check this actually, whether lambda equals lambda bar, and this you see in the most cases easily. Then you get it for all operators. And recently we were checking whether something similar is true for mild V star homomorphisms. And indeed, under mild technical assumptions, if every functional in K prime, K star is a mild V star homomorphism, then every positive operator is a mild V star. It's a similar technique. It works there for this new notion of mild V star as well. And the same if every mild V star homomorphism is a V star homomorphism in K star, then the same is true here. So this translates easily. That's why it's enough to check just the dual cone. Yeah, this was very recent work. So let's again look at the scheme. This you already know, this the lower 4 objects. And lattices, these are all the same. Lattices, these are the same. And now I convinced you, I hope at least, that they are distinct in ordered vector spaces. There are more operators that are considered in class. So in vector lattices, there is a notion of order convergence. So there is a notion of order continuity. And in lattices, these order continuous Reisz homomorphisms were investigated as well. And it was shown that in Reisz homomorphism, in Reisz spaces or in vector lattices, this is exactly the same as complete Reisz homomorphism, meaning I have the set with increment 0, I apply the operator, and the image has also increment 0. This is exactly the same. I just mentioned this, that you see that the theory is bigger, and here there are some open questions. But I think this scheme here, the lower 4 objects, we have kind of understood now. So far we have all properties, all definitions, all properties of these operators and how are they related. And there was a second issue in the classical case on spaces. How long do I have done? Just let me mention last 2 words. The second question was, can we represent these type of operators in spaces of, when we are in spaces of continuous functions? And there were so forget this. The answer is yes. In fact, we can find such a representation for these objects for complete Reisz homomorphisms, for Reisz homomorphisms, and for the others we don't know yet. So this is a list of open questions we have, and here shall I end? Maybe, yeah. Okay, maybe I should finish. This is just to answer the last question between joint preserving operators and Reisz homomorphisms. This can be so this equivalence is given under certain conditions. So we also consider this. Since I have to finish now, I cannot tell you about joint preserving operators in the groups. I just want to mention that there is a theory on operator semigroups on Banach lattices, and with these techniques, especially the relation between the semigroup and the generator, with these techniques we can do also things in ordered Banach spaces, and this is a very recent and active field of research. Okay, thank you very much for your attention.
Thank you, Dr. Kalauch, for your very insightful presentation. Any questions? Oh, anybody who has any questions online? So I just want to quickly make a comment. How many of you have done the Young-CF system or positive linear system last year? Okay, so some of you have done that, right? Have you seen any similarities with the partial order vector space? Primums, infimums, convex cones? Yes, interior points. Okay, so this is a sort of thing that you can take that in here. Okay, that's a continuation. And I just have a quick question for Doctor. So I'm sure lots of, because this is for the benefit of our students, they are all honor students. So I'm sure you're wondering, what can we do with this space in terms of application?
In terms of application, I mean, you just mentioned the positive system. Probably you have done these standard initial value problems, yeah? X of 0 is something. You know those, I suppose, yeah? So just a system of ordinary differential equations. You have considered those, right? And for applications, for example, in economy, you want, I mean, what happens here? Yeah, you start. Oh, doesn't work. Other options, okay. So in economy, all your goods are positive, yeah, or positive identities. Or in biology, when you have, when you look at bacteria or whatever, you have positive objects, and you start somewhere here with your x0. And when you model such a system, of course, you want you want something sensible for your economy or for your biology, namely that when the trajectory starts here, it should stay in your positive part of the space, yeah, in a positive cone. That is the standard cone in R3 I was drawing here. So each coordinate should be positive. You want the trajectory, so your solution here should stay in the positive cone. But for some applications, you run out of these very nice cone. The cone is some kind of this polyhedral cone, like in R3 or in R4, an optimization. So you have other cones here, but you want to have the same positive systems. Namely, that means if this is in K, then your solution is in K for all T, yeah, in R plus. So for all your times, you want to stay in the cone. And these positive linear systems, they have very nice properties. And this is because positive operators or other operators here, we need only positive off-diagonal operators, but they are closely related and they have nice spectral properties. And the spectral properties of these matrices here, in the simplest case, it's a matrix, or in the more general case, it's a linear positive operators. They have very nice spectral properties. All the Brian von Sarkalin theorems, classically the Perron-Corbinian theorems, I would say that the spectral radius is an eigenvalue, and you have positive eigenvector, and the positive eigenvector gives you at the end the long time behavior of your system. That's why these positive systems are so nice. But the problem is, you run out this cone here is a lattice cone. But if you, for practical reasons, have other cones here, can you end up in these ordered Banach spaces? You go out of your lattice theory, you need this theory on ordered vector spaces. Yeah. And this generator here belongs then closely to the properties of the semigroup you generalize by, or you generate by these generators. There are relations between so these disjoint preserving semigroups are investigated very well, and in the generators band preserving operators such results. It is then related to this theory. Okay.
Any more questions? Any questions at all? Good. You have all done something.